Hey, this is Mr. Aiden. Today we're going to be going through the 2021 AP Chemistry Free Response Questions number 2. This is from the 2021 AP Chemistry exam. If you're a teacher or you're a student and you want to get some extra help for your students or for yourself, go to MrAiden.com. I have hundreds of multiple choice questions. I got free response questions. I got extra review sheets, everything you need to get your 5 on your AP Chemistry exam. But let's get to this exam. You can see the question starts off with a mass spectrum of silicon. And anytime you see mass spectrum, you want to go to the mass number or the number of neutrons and protons. We know that the mass of an element is from the protons plus the neutrons. The electrons weigh essentially nothing comparatively to that proton and neutron. And you can see the most abundant isotope of silicon is silicon-28. Silicon-28. Now, if you look on your periodic table, you'll find silicon has 14 protons. And because it's element number 14, that's its atomic number, which means it must have 14 neutrons, which adds up to your mass of 28. You can see isotope silicon-29 has 1 more neutron, so 15 neutrons. Silicon-30 has 16 neutrons. But you can see on this one we have the most abundant isotope is silicon-28. And then we want to know the ground state electron configuration of silicon. So we're going to take a look at that electron configuration all the way up to silicon. And so that ends up becoming 1s2, 2s2, 2p6, 3s2, 3p2. You can take a look. 2 and 2 is 4, 6 is 10, 14. That gives you element number 14 for a neutral element for a ground state electron configuration of silicon. So we ended up having part 1, A1, and you can see part 2 right here. Just 2 very easy atomic structure problems. But then we go from atomic structure to intermolecular forces. And you can see I've actually seen some people have videos on the internet, and they're wrong on this. They're way wrong. And their reasoning, and I don't understand how they can teach AP Chemistry and still get this wrong. I can see how students might get this wrong because you have one compound with silicon, another with silicon, and you're trying to take a look at interparticle or intermolecular forces here. Now you can see SiH4 is going to boil, but SiO2 will remain a solid. That's a big key word right there, is that it's a solid. SiH4 boils, which means it's a gas. SiH4 must be a gas, which means it must have a very weak intermolecular forces. It only has London dispersion forces. Make sure on an AP exam you write out London dispersion forces, then you can put in parentheses LDF, and you can use LDF after that. But it has London dispersion forces. It's a tetrahedral shape, 109.5 degrees. And you can see that LDF tetrahedral shape, 109.5 degrees, sp3 hybridized. It's only got London dispersion forces, very weak intermolecular or interparticle forces. It's probably best to use the term interparticle forces here because we're looking at particles, interparticle forces. But SiO2 is a solid, which means it has very strong forces, very strong interparticle forces. And we think, is it ionic? No. Is it metallic? No. It is a covalent network solid. It's got strong interparticle forces. It's got a strong network, which means it will still remain a solid, whereas the SiH4 will be a gas. Okay. Then we want to know a balance equation for SiH4. So SiH4 is our reactant. It's going to decompose to form solid silicon and hydrogen gas. We're just looking at our solid silicon, hydrogen gas. We're going to put a big 2 right there, so it's a 1:1:2 ratio in order to balance that out. And this balance reaction, again, if you're part of MrAiden.com, this is very similar to a lot of our Big 25 reactions that you should be able to practice and know. We're going to need that balance reaction of SiH4 breaking down into solid silicon and 2H2 gas. Anytime they have you do a balanced reaction, you're probably going to use that in some sort of molar ratio or some sort of stoichiometry or some sort of even thermodynamics or kinetics, something where you're going to use that. And the first thing they ask us in part D, after giving us a table of absolute entropies, is explain why the molar entropy of silicon is less than that of hydrogen gas. And let's just think about that. Si silicon solid has less entropy, we want to spell the word has with one S, so has less entropy as compared to the hydrogen gas due to the very low dispersion of particles. Solids are very ordered, aren't they? Solids are very ordered in their particles. They're very ordered substances with very low disorder. As well as arrangements of particles. Okay. H2 is a gas. Hydrogen is a gas and has a greater dispersion of particles. It has a great amount of disorder in its particles because it has higher speeds, more arrangements. The worst thing you can do in this type of problem is just go Si solid has less disorder. H2 has more disorder. A lot of people just see entropy and go, it is disorder. No, it's more than just disorder. We have to explain for that AP reviewer. We have to explain the number of arrangements of particles, the speeds, the disorder, the order, all of those different things help to give you a fuller answer. Now the part E. Part E asks you to calculate the value for the delta S. So what do we do with delta S? We know delta S for our reaction is going to be the sum of the delta S's of the products minus the sum of the S's of the reactants. Okay, this is on your equation sheet. So we got to go to our products. Our products are silicon, which is 18 joules per mole Kelvin, plus 2 times 205 joules per mole Kelvin, minus my 2 times the 131, because that's the hydrogen gas. Those are my products, minus the reactant, which is 205 joules per mole Kelvin. And so if I was doing this, I would literally put 18 joules per mole Kelvin, 131 joules per mole Kelvin, 205 joules per mole Kelvin. I would take the time, and you can see it's positive 75 joules per mole Kelvin. That entropy is positive, and why is that entropy positive? We are going towards more disorder, more arrangements of particles. We're going from one substance into a solid and a gas. Yes, the solid is more ordered, but the gas has 2 particles that are very, very disordered. And so that's why the delta S is positive 75 for part E. Part F it shows up on every single AP chemistry exam, and this one is if the reaction is thermodynamically favorable. What do we know about thermodynamically favorable? That means your delta G is negative, and so right away you might think this is a delta G equals delta H minus T delta S problem. I know my delta S is positive 75. I know my temperature. I don't know my enthalpy, my delta H though, and they want to know explain why the reaction only occurs at higher temperatures. And so this is called kinetic control. This is called kinetic control because what's happening, this shows up on every AP exam. If the reaction is only favorable at higher temperatures, the delta G is negative, but only occurs at those high temperatures. So if it's always favorable, but at all temperatures, but it's only going to react at a high temperature. That must mean there is a high activation energy. It is known to be under kinetic control. It's known to be under kinetic control, which means that high temperature needs to be achieved. So that it overcome the high activation energy barrier. And so you can see how we have a high activation energy barrier. Even though it is favorable, we still need to reach that barrier. And even then, those particles need to orient at the right places, need to collide, and so you need all that collision theory happening. Now we go to part G. Part G, you can see how AP Chemistry uses everything. We're back to atomic structure here. And you can see the partial photoelectron spectroscopy of silicon. This gives us our electron configuration, and we want to draw the missing peak. And so right away, the highest energy is the 1s2. And why is the highest energy the 1s2? It's because these electrons are closest to the nucleus. These electrons are experiencing the most nuclear charge, so the most attraction. Then the attraction gets less as we get further away from the nucleus. So 2s2, we've got 2p6, we have 3s2, and then we have our 3p2, which is going to be a height of 2 because there's 2 electrons. It's 3p2. It's going to be less energy because those electrons are further away from the nucleus. And you can see H jumps right into it. Keeps going with atomic structure. It says, explain why the first ionization energy. Now we got to know what first ionization energy is. That's the energy to remove an electron. And why is the first ionization energy of germanium lower than that of silicon? Well, this is a vertical trend. If you are part of MrRating.com, this is a vertical trend. And germanium, you can see, this is coming down to Coulomb's law. Coulomb's law is a very, very, very important law. And you can see germanium's valence electrons are at a greater distance as compared to that silicon. When compared to silicon, this means that germanium's valence electrons are at a greater quantum energy level, and so therefore these valence electrons are less attracted to the nucleus. Therefore, if it's less attractive to the nucleus, it takes less energy to remove this valence electron. And you can see silicon's valence electrons are closer to the nucleus. They're at a lower quantum energy level. They're more attracted to the nucleus because those electrons are closer, and so it takes more energy to remove these valence electrons. And so you may really have to work on giving a full orbed response for that AP reviewer, but just go logical and it will work. And then we finish this problem number 2, with another atomic structure problem, but this is more of a calculator type problem. You can see they gave you the wavelength. This wavelength is 4.00, there's 3 significant digits there, times 10 to the -7th meters. Okay, and we want to know the energy. So we're going to have to use both these equations. And so the speed of light, you can see the speed of light is 2.998 times 10 to the 8th meters per second is equal to wavelength, 4.00 times 10 to the -7th meters, times the frequency. That's the speed of light equals wavelength times frequency. That's this second equation right there. So we can find our frequency. Once we find our frequency, then we can plug that in to energy equals h times that frequency. This h is Planck's constant. That's 6.626 times 10 to the negative 34th joules seconds times that frequency that you find. And so energy, when we do both those equations, the energy ends up becoming 4.97. 4.97, I'll clean that up a little bit. 4.97 times 10 to the negative 19th joules. And that is your energy for this wavelength of light. Now, the interesting thing is my students that take me for physics, that have had me for physics for a long time, they know we can combine these two equations together by doing energy equals h times the speed of light over the wavelength. And so we can combine both of these equations together. My students end up just knowing this equation from these two. And so if you want to do this just in one step rather than two steps, we take 6.626 times 10 to the negative 34th times 2.998, 2.998 times 10 to the 8th over the wavelength of 4.00 times 10 to the negative 7, and that ends up giving me 4.97 times 10 to the negative 19 joules. I like doing it that way. You can do it in two steps or just in one. Either way, you get the same answer, 4.97 times 10 to the negative 19 joules. And that is the 2021 AP Chemistry Free Response number 2. Thanks, guys. I'll see you for number 3.